Okay, let's talk about thermal expansion and thermal stress now. So let's say we have some sort of a molecule here, represented by these green atoms. This could be any shape or size or anything, um, and it's connected together with some forces, some bonds between these molecules, which I'll just represent them as kind of like a spring. So we have some springs here, okay, um, and let's say that I put some heat into this. Now, heat is a form of energy, right? Thermal energy. So I put some heat into it, and what's going to happen is that now there's going to be more energy in this molecule, right? So what happens is, these molecules will sort of like twist and rotate a little bit. They'll kind of, do some rotations there, but they'll also kind of start to oscillate kind of back and forth and maybe around like this, right? Maybe going like that, maybe going something like this, and it's going to kind of oscillate here a little bit, and the molecules around them will oscillate as well. And effectively, they're kind of like they're bigger. Maybe it's getting a little bit smaller too, but as it kind of bounces back, it it takes up a larger space kind of in total, and its total motion is going to take up a larger space, and the ones next to them are also going to take up a larger space, right? So when you put energy into something, the result is that if I putting all these molecules together, the material, could be a solid, a fluid, or a gas, it'll expand, it'll get bigger, it'll take up more space, because then there's more energy for these things to kind of move around a little bit. If you were to think about this as like a gas or something, you put energy and those molecules just start flying all over the place, right? So this is true for a solid, a liquid, or a gas. When you put heat into it, heat energy, then it will cause the material to expand, okay? And actually, one of the biggest components of sea level rise, due to global warming, is the expansion of seawater. Not just how much water is added, but the actual expansion of it itself. The water that we have is going to take up more space. Okay. So I wanted to look at just linear expansion as well as volumetric expansion here. So if we have something, we're just looking at it linearly. So linear expansion. So, if we have something that's like this long, I don't know, something like a steel rod or something like that, and then you put some heat into it and it gets a little bit longer, right? So then I have some change in length, delta L, okay? And then I have some starting length, I'll call this L naught, okay? And I'm just worried about how long it's getting. Technically it's going to also, expand out this way as well, a little bit here. It's going to expand in all directions, but let's say I'm just mostly interested in how much that it's getting longer. So the change in length is equal to some alpha, which is our coefficient of linear expansion, times how long it was originally, times the change in temperature. Okay, so this change in temperature here, oftentimes alpha is given in like per Kelvin or per Celsius. You kind of have to look to see what alpha is given in for your delta T, if it needs to be Fahrenheit, Rankine, or Kelvin or Celsius. And quick note, the size of 1 Kelvin is the same as the size of 1 Celsius, right? So if we're given a temperature change in Celsius, but the alpha's in something per Kelvin, we can use those without any sort of changing, because the size is the same. So change in 1 temperature Kelvin is the same in change in 1 temperature Celsius, right? And the same thing would be true for Rankine and Fahrenheit. They're the same size, temperature changes. Okay. This L naught, the more material we have, the more it's going to expand, right? So this is why L naught is important. If it's only like 1 inch long, it's not going to expand 10 inches. But if you have it, like a couple miles long, it's probably going to expand, several feet, right? And then alpha, this is the coefficient of linear expansion. So this has to be determined experimentally. And this is in your book in table 13.2, that table. And, it's measured experimentally, kind of like friction is. And, it depends on these bond types, right? So it depends on, what the this bar is made out of, and et cetera, right? So I have, if steel is going to have a different coefficient of linear expansion than, say wool or something like that, right? Okay, so here we have, this is our change in length, which is the coefficient of linear expansion times the initial length times the change in temperature, right? Oftentimes this delta T needs to be in Celsius or Kelvin because this is something like per Kelvin. We can also look at volumetric expansion. So there's another one. If I look at the change in volume, a volumetric expansion is beta, which is a coefficient of volumetric expansion times our times the starting volume, V naught, times the change in temperature here. So this is basically the same equation, except we have here, this is the coefficient of volumetric expansion, as opposed to the linear. And this is in table 13 point, also actually table 13.2 as well. So both linear as well as volumetric expansion coefficients are in table 13.2. One of the things you might see here, actually, if you have, a big temperature difference, maybe between winter and summertime in places, or even just between day and night, you might see like roadways and things that they have these gaps in here. These are called expansion gaps because it needs to expand. You don't want it to expand against, whatever's holding it up, right? Which is gonna, make the road break or the bridge break or something like that. So oftentimes you see these kind of over bridges, and so these are called expansion joints to kind of deal with the expansion that happens when it heats up, relative to being cold. So we can actually talk about the stress produced by thermal expansion, which is really what they're trying to avoid here is the thermal stress, the force per area, as opposed to just the expansion itself. Allow it to expand. The only way to stop it from expanding would be to keep the temperature constant, right? Or get a material that has a very, very low alpha or beta. So we can actually look at the thermal stress, and we can go back to just remembering the equation for linear stress, right? So for linear stress, we had force per area, this is stress, was equal to Young's modulus times the strain, right? Delta L over L naught, right? If we rearrange this, then let's solve for our strain. Actually, let's go back to the linear expansion. Let me come back to this. Delta L equals alpha L naught delta T. Let's get delta L over L naught. So we can say here delta L over L naught is equal to alpha delta T, right? So this is just dividing both sides by L naught, right? So the strain, the thermal strain, is alpha delta T, and the stress is Young's modulus times the strain. Well, I can just take the strain, plug it in there, right? And so then I have the stress, force per area, would be Young's modulus times the coefficient of linear expansion times the change in temperature. This is the thermal stress, the linear thermal stress. It would just be beta here for volumetric, right? So this is we're interested in just kind of linear. So this is what we'll call the thermal stress.